Central force. What is a central force? In the name itself, it is specified. It acts towards a center or away from a center. And we can represent this central force as F vector is equal to plus or minus F of r cap. So this central force will be a function of r only, and if the direction between F vector and r cap vector is 0 degrees, then it will be positive, and if the direction between F vector and r cap vector is 180 degree, then it will be negative. Here F vector and r cap in the same direction, right? And here F vector and r cap vector are in opposite directions. These are two previous set questions. See, what is the answer of first question? Here you can see a central force experience a force directed along the radial direction only. So this one is the correct answer. And for the second question, in a central force field, the force is always directed along the radius vector and depends only on the distance from the center of force. So these are the correct answer. Okay. So these are very simple questions, right? Properties of central force. First property, del cross F will be equal to 0. That is, curl of a central force will be equal to 0. And if curl of a force is 0, then we can say it will be a conservative force. And in a conservative force field, the total energy is conserved. That is, it will be a constant. Second property, torque will be equal to 0. That is, we know torque is the rotating force and torque is equal to R cross F. That is equal to RF sin theta. And I told you the angle may be 0 degree or maybe 180 degree for a central force. So for the so what we get? We get sin 0 or sin 180 equal to 0. So we get torque equal to 0. Third property, angular momentum L is conserved, or we can say it is constant. I will give you some explanations. We know linear momentum is P, and we know force is equal to dP by dt. Similarly, we know angular momentum, that is L. So torque will be equal to dL by dt. And here I told you the torque is equal to 0. Therefore, L must be equal to a constant. That is, L is constant. And fourth property, the relation between force and potential. That will be the force F of R will be equal to negative gradient of potential. That is dou V of R by dou R, where V of R is the potential. See, these are the various set questions and all are related to central force. In the first question, it is discussing about planetary motion, and you know planets are moving under gravitational force, and we know gravitational force is a central force, right? So the first question is, which of the following quantities is conserved and why? I told you angular momentum will be the conserved quantity because there is no external forces acting on that system. And for second question, you see again the answer is angular momentum is conserved. Here also angular momentum is conserved. An example problem. The transverse velocity of a particle under central force varies with r as. This is the question. So here we know what is the transverse velocity. Transverse velocity is equal to r theta dot, and we know L equal to m r square theta dot. So we can say theta dot is equal to L by m r square. So we can replace this theta dot, that is r into theta dot is L by m r square. So we can cancel this r and r. So we get it is equal to L by mr. So the transverse velocity is proportional to 1 by r. Motion under central force. We discussed some of these ideas in the Lagrangian itself, and I told you what will be the trajectory of a motion under central force. I told you the trajectory will be plane curve. What is a plane curve? It is like this one. See, the particle move in a plane. So suppose this is a particle, and then we can represent this by r and this by theta. So for every planetary motion, the trajectory is a plane curve, because every planetary motion is under central force. Okay, and I told you this is a plane polar coordinate system. So there is two coordinates, one is r and theta. And what will be the possible velocities? See, maybe the particle can move in this direction. So there is a velocity, that is r dot, or this particle can move in this direction. So this velocity will be r theta dot. So two velocities are there, one is r dot and one is r theta dot. Where this r dot velocity we call as radial velocity, and this r theta dot velocity we call as transverse velocity. So we can construct the Lagrangian, that is Lagrangian is equal to 1 by 2 m v1 square plus v2 square. Here you know the angle between these two velocities is 90 degrees. So when we are squaring and adding the velocities, we get r dot square plus r square theta dot square minus v of r. Here you can see this Lagrangian is not a function of type. So we can say energy, total energy will be equal to a constant. We already discussed this ideas, right? And second one, and you know this theta is a cyclic coordinate. So p theta, that is equal to dou L by dou theta, will be equal to a constant. And what is this p theta? P theta is nothing but angular momentum L, that is angular momentum L is constant, or it is a conserved quantity, that is L equal to m r square theta dot is a constant, right? So there are two important points. One is total energy is a constant, and other is L is equal to mr square theta dot is a constant. Okay. This one is an example problem, and the question is to find out the transverse velocity. We know what is transverse velocity. It is equal to r theta dot, and under central forces we know what is the value of theta dot. We know L is equal to m r square theta dot. So we can find out theta dot is equal to L by m r square. So on substituting this value, that is r into L by m r square. So r and r cancels, remaining we get L by mr. That is, it is proportional to 1 by r. Okay. Effective potential. By using the idea of effective potential, we can convert a 2D problem into 1D problem. We are dealing with the plane curve. So the particle motion is represented by two coordinates. One is r and the one is theta. So this is a 2D problem. We need two coordinates. One is r and the other is theta. And by introducing this idea of effective potential, we can reduce it into 1D problem. And in 1D problem, it will be only function of r. There will not be any theta terms. I tell you how we can reduce a 2D problem into 1D problem by using the effective potential. First of all, we know the total energy, that is E equal to kinetic energy plus potential energy. And kinetic energy is equal to, generally it is half mv square plus here potential is v of r. And you know there is two velocities, one is radial velocity and one is transverse velocity, that is r theta dot. Okay, so we get this is equal to 1 by 2 m into r dot square plus r square theta dot square plus v of r, where this v of r is the actual potential energy. Okay, and we know in a central force motion, the angular momentum is conserved and it is equal to mr square theta dot. So we can find out theta dot is equal to L by mr square. Now I am substituting this for theta dot. So I get total energy E equal to 1 by 2 m r dot square plus r square into L square by m square r raised to 4 plus v of r. So I can cancel this r square and 1 of r square here. So we get total energy E equal to 1 by 2 m r dot square plus L square by m square r square plus v of r. Now I am expanding this equation, so I get E equal to 1 by 2 m r dot square plus L square by 2 m r square plus v of r. So here you can see here there is a velocity term, so this is definitely kinetic energy. And here there is no velocity term, so this energy will be potential energy. And here I already told you v of r is the actual potential energy. So this entire term is effective potential energy. Now you just look into the equation for energy. Is there any function of theta? No. The equation of energy is totally a function of r only, right? So earlier the total energy is a function of r and theta, but by introducing the effective potential, the problem is reduced to 1D. That is, there is only one variable, that is r only, right? So I can rewrite this equation for energy E as 1 by 2 m r dot square plus v effective. And what is this v effective? V effective is equal to L square by 2 m r square plus v of r. And earlier I told you one thing, that is f equal to minus dou v by dou r. So this is valid for f effective also, that is f effective will be equal to minus dou v effective by dou r. So what we get? We get f effective is equal to minus dou by dou r of L square by 2 mr square plus v of r. So what we get? We get f effective is equal to L square by m r cube minus dou v of r by dou r. These are very important equations. Please remember. Okay. This one is a previous set question, and this one is a very easy problem. You see, the effective potential is equal to L square by 2 mr square plus V of r. And we know, and in the given problem, they specified the particle is moving in a attractive central force field having inverse square dependence on r. That is gravitational field, right? So in a gravitational force field, we know the potential, that is V of r is equal to minus g m by r. This is equal to, we can call, minus k by r. In the question itself, it is specified that is k is constant of proportionality for the force. So this will be minus k by r. So by substituting this value here, you get the answer, right? That is option B. Example problem. One mass is in a circular motion like this. Okay. Then what will be the total energy, E total? See, this is some kind of central force motion. So the force is acting only in this direction, right? We know the equation for E total, that is equal to half m r dot square plus V effective. So here, this is the r, and in a circular motion, r is equal to a constant. Therefore, r dot is equal to 0. So this entire term is equal to 0. So for a circular motion, E total will be equal to V effective only. Okay. And one more question. What is the F effective here? That is effective force here. In a circular motion, there are two forces acting, and this force is centripetal force, and one more force is there. This is centrifugal force. Okay. So these forces are equal and opposite. So they cancels each other, and we get F effective is equal to 0. This one is a previous net question. And in the question, two particles of identical masses. So mass is m, this also mass m. They are move in a circular orbit under central potential. It is given V of r equal to half k r square. And L1 and L2 may be their angular momenta, and R1 and R2 are the radius. And the given L1 by L2 is equal to, and we have to find out R1 by R2. So this is the question. We now, in a circular motion, effective potential is equal to 0 because centripetal force and centrifugal force will cancel each other. So effective force is equal to 0. And we know F effective is equal to minus dou V effective by dou R. So here F effective equal to 0. Therefore, dou V effective by dou R is also equal to 0. And what is this V effective? We know V effective is equal to L square by 2 mr square plus V of R, right? So we can find out the F effective, that is equal to minus dou V effective by dou R, that is equal to minus dou by dou R of L square by 2 m r square plus V of R. Here this V of R is given, that is equal to half k r square. So what we get? We get F effective is equal to L square by mr cube minus k r. And we know F effective equal to 0. Therefore, we can rewrite this equation, that is L square equal to k r into mr cube. That is L square equal to kmr raised to 4. Therefore, L will be equal to root kmr square. Right. So here we have to find out L1. So L1 will be root km r1 square and L2 will be equal to root km r2 square. Therefore, we get L1 by L2 is equal to r1 square by r2 square. And in the question they have specified L1 by L2 equal to 2, that is equal to r1 square by r2 square. So we get r1 by r2 is equal to root 2. So this is the answer. This is one way of solution. You can solve this problem using +2 physics also. I tell you how you can do it. Solution using +2 physics. Okay, here you leave about this orbit and all. See, in the question it is given the identical masses move in a circular orbit. Here this word, the circular orbits and all are making some confusions because you think about planetary motion and the planetary orbits and all. So you just think one thing only, that is it is a circular motion, and we know all about circular motion in +2 physics itself. For a circular motion we know the force is equal to mv square by r. That is the centripetal force. Some centripetal force is required for the circular motion, and that F is equal to mv square by r. Right. And in the question they given the potential, and from potential we can find out the force, that is equal to minus dou v of r by dou r. So we get the force in the given problem as it is equal to minus kr. So this force and this force should be equal because it is a circular motion, right? So we get mv square by r is equal to kr. Here I am taking only the magnitude. So from this equation I can rewrite this equation, that is v square by r square is equal to k by m, and k by m is a constant. So v square by r square is a constant. So we can say v by r is equal to a constant. Now we know about angular momentum. In a circular motion, what is it? We know L equal to mv r. That is, if this mass is moving with a velocity v and this is r, then it will be mvr. So from this equation I can write for v, that is v will be equal to L by mr. Now I am dividing this v by r, so I get v by r equal to constant, so that is equal to L by mr square. So this is equal to a constant. So I can write L1 by m r1 square will be equal to L2 by m r2 square. That is L1 by L2 is equal to r1 square by r2 square. Here in the question L1 by L2 is given, that is 2. Then r1 by r2 all square is equal to 2. Therefore we get r1 by r2 is equal to root 2. So even you don't know much more about central force and all, then also you can solve this problem just by +2 physics. A small note for you. For circular motion or any motion, we know the total energy will be kinetic energy plus potential energy. And in the case of a circular motion, this potential energy will be function of r, that is v of r. That is kinetic energy plus v of r is equal to 1 by 2 m r dot square plus L square by 2mr square plus v of r. So we can cancel this v of r and v of r, and we know in a circular motion, that is like this one, a mass is moving. So in the circular motion, you know this is the radius r and this is equal to a constant. So r dot is equal to 0. So this time will be equal to 0. So we get kinetic energy in a circular motion is equal to L square by 2mr square. This is always true for circular motion. Next topic is equation of motion in central force. We know the Lagrangian in a central force, that is L equal to 1 by 2 m r dot square plus r square theta dot square minus v of r. And when considering the equation of motion, that is we know d by dt of dou L by dou r dot minus dou L by dou r equal to 0. Then we get this is equal to m r double dot minus m r theta dot square plus dou v of r by dou r equal to 0. So I can take this time to RHS of this equation, that is m r double dot minus m r theta dot square equal to minus dou v of r by dou r. We are familiar with this term, that is this is nothing but f of r, that is the negative gradient of potential, right? So I can rewrite this equation as f of r equal to m r double dot minus m r theta dot square. And from this Lagrange's equation, we know theta is cyclic coordinate and therefore p theta is a conserved quantity, and we know p theta is equal to dou L by dou theta dot, and that will be equal to m r square theta dot. So we can find out theta dot, that will be equal to p theta. P theta here it is angular momentum, so we can write L by m r square, where this L and m are constant. So I am writing it in another form, that is h by r square, where h is equal to L by m. And I am defining a term, that is 1 by r, that is equal to u. So I can rewrite this equation of theta dot, that is equal to h u square. Therefore I can rewrite this equation for f of r, that will be equal to m r double dot minus m, where r can be replaced by u, into theta dot square is h square u square, that is f of r equal to m r double dot minus m h square u cube, right? Now I want to find out value of r double dot. We know r dot is equal to dr by dt, and I can rewrite this equation as dr by d theta into d theta by dt. So here d theta and d theta will cancel and we get dr by dt itself, right? And we know d theta by dt is nothing but theta dot. So I can rewrite this as theta dot into dr by d theta, where we already found the value of theta dot, that is h u square dr by d theta. Now we have to find out the value of this dr by d theta. To find out this value of dr by d theta, let us consider r. We know r is equal to 1 by u. Therefore dr by d theta will be equal to minus 1 by u square du by d theta. So now we got r dot in terms of Here we got this r dot in terms of dr by d theta. So I can rewrite this as r dot is equal to h u square, and dr by d theta we found here, that is equal to minus 1 by u square du by d theta. That is, we get r dot is equal to minus h du by d theta. Now we have to find out r double dot, that will be equal to minus h d by dt of du by d theta. Here I can change the order of differential, that is, I can rewrite this as r double dot is equal to minus h d by d theta of du by dt. Again I am rewriting this as r double dot equal to minus h d by d theta into du by d theta into d theta by dt, where d theta by dt is theta dot, and we know theta dot is equal to hu square. So what we get? We get r double dot equal to minus h square u square d square u by d theta square. So now we can substitute this in our equation of f of r, that is f of r equal to m r double dot minus m h square u cube. Now I am substituting this value here, so I get f of r equal to minus m h square u square d square u by d theta square minus m h square u cube. Now once again I am rewriting this one, that is, here some common terms are there, see. So I am taking these common terms outside, that is m h square u square into d square u by d theta square plus u. And again I am doing some rearrangement. I am taking this term here and taking these terms to the LHS. So I get d square u by d theta square plus u equal to minus f of r by m h square u square. This is the differential equation for motion under central force. Actually, you don't want to remember all the derivation, you just remember the final equation. Here h is equal to L by m and u is equal to 1 by r. This is very important. Okay. Application of differential equation of motion for orbits. That is, a trajectory will be given in the question. Then you are asked to find out corresponding force law. One example problem. The trajectory is r equal to e raised to theta, and find out the force law. Here we know what is the differential equation for orbits, that is d square u by d theta square plus u equal to minus f of r by m h square u square. Here the question is to find out this f of r value. Okay, and we know the u is equal to 1 by r, and that is equal to e raised to minus theta. So first you have to find out this one, d square u by d theta square. So first you have to find out du by d theta, that is equal to d by d theta of u, that is e raised to minus theta, and the derivative of e raised to minus theta is minus e raised to minus theta. Now we have to find out d square u by d theta square, that is equal to d by d theta of du by d theta, that is minus e raised to minus theta, and we get this is equal to e raised to minus theta. Now we can substitute these values in this equation. So we get e raised to minus theta plus e raised to minus theta equal to minus f of r by m h square u square. where we know u is equal to e raised to minus theta. So u square will be e raised to minus 2 theta. Now I am going to rearrange this equation. I am collecting this theta terms in the LHS of this equation. That is e raised to minus 2 theta into e raised to minus theta plus e raised to minus theta equal to minus f of r by m h square. Here this is equal to 2 e raised to minus theta. So we get this is equal to e raised to minus 2 theta into 2 e raised to minus theta equal to minus f of r by m h square. Therefore, the force law, that is f of r equal to minus 2m h square e raised to minus 3 theta, where we know r equal to e raised to theta. So 1 by r cube is equal to 1 by e raised to 3 theta or e raised to minus 3 theta. So we get f of r is equal to minus 2m h square by r cube. So this minus sign represent it is attractive force, and this is a inverse cube law. Because of 1 by r cube. Okay. Another example problem. The trajectory is given, that is r equal to a e raised to b theta. Find force law. So what is the differential equation for orbit? That is d square u by d theta square plus u equal to minus f of r by m h square u square. Here we know h is equal to L by m, right? And u is equal to 1 by r. Here u is equal to 1 by r, that is we get 1 by a e raised to minus b theta. Now we have to evaluate this term, that is du by d theta, that will be equal to d by d theta of 1 by a e raised to minus b theta, and we get this is equal to 1 by a e raised to minus b theta into minus b. Now we have to find out d square u by d theta square, that is equal to d by d theta of minus b by a raised to minus b theta. So we get minus b by a into e raised to minus b theta into minus b. So we get this is equal to b square by a e raised to minus b theta. Now we can substitute these values in this equation, that is we get b square by a e raised to minus b theta plus u is equal to 1 by a e raised to minus b theta equal to minus f of r by m h square u square, that is into a square e raised to 2 b theta. So we have to find out this f of r term. So I am going to rearrange this equation. That is f of r equal to minus b square by a e raised to minus b theta plus 1 by a e raised to minus b theta into m h square by a square into e raised to minus 2 b theta. Again I am rearranging, that is minus m h square by a cube into b square plus 1 into e raised to minus 3 b theta. So we get f of r equal to minus m h square b square plus 1 by a cube e raised to 3b theta. In the question it is given r is equal to a e raised to b theta and r cube will be equal to a cube e raised to 3 b theta. So this is nothing but r cube. So we get f of r equal to minus m h square into b square plus 1 by r cube. So this is the force law corresponds to given trajectory, that is r equal to a e raised to b theta. Another example problem, the trajectories are equal to a cos theta. Find force law, that is f of r. So, d square u by d theta square plus u equal to minus f of r by m h square u square. And we know u equal to 1 by r. Therefore, it is equal to 1 by a cos theta. 1 by cos theta is nothing but sec theta. That is 1 by a sec theta. Now, we have to find out this term first. That is du by d theta. That is d by d theta of 1 by a sec theta. I think you know the derivative of sec theta. That is 1 by a into sec theta into tan theta. Now, we have to find out d square u by d theta square, that is equal to d by d theta of 1 by a into sec theta into tan theta. That is equal to, we can take 1 by a outside into d by d theta of sec theta into tan theta plus sec theta into d by d theta of tan theta. I think you know this derivative, that is d by d theta of sec theta is sec theta into tan theta, and d by d theta of tan theta is sec square theta. Now we can substitute all these values in this equation. So what we get? We get 1 by a into sec theta tan square theta plus sec cube theta plus u. U is equal to 1 by a sec theta equal to minus f of r by m h square u square. That is a square by sec square theta. Here you can see we have a common term, that is 1 by a. So I can again rearrange this equation, that is 1 by a into sec theta into 1 plus tan square theta plus sec cube theta equal to minus f of r by m h square a square by sec square theta. Here we know 1 plus tan square theta is nothing but sec square theta. So we get 1 by a into sec cube theta, that is 2 sec cube theta equal to minus f of r by m h square a square by sec square theta. So now we have to find out the force law, that is we have to rearrange this, that is f of r equal to minus 1 by a to sec cube theta into m h square sec square theta by a square. That is f of r equal to minus 2 by a cube m h square 6 raised to 5 theta. In the question it is given, that is 1 by r equal to sec theta by a. So I am multiplying this with so here one a square is missing, so I am dividing with a square and multiplying with the a square. So we get f of r equal to minus 2 m h square a square by r raised to 5. So this is the force law corresponds to given trajectory. Some trick to find the solutions. If in the question they are asked to find out the proportionality of f of r, that is it proportional to 1 by r square or it is proportional to r square or something. If the question is to find out the proportionality, then you can use these tricks. First trick, if the given trajectory is r equal to e raised to plus or minus n theta, n may be any value 1, 2, 3, etc. Then by solving the differential equation for orbit, you get f of r is proportional to minus 1 by r cube. This is always true. For example, in the earlier example problem, I told you the trajectory is r equal to e raised to theta. And what we get f of r? We got f of r equal to minus 2m h square by r cube. See? It's proportional to r cube. Here n is equal to plus 1, right? And another case, that is r equal to a e raised to b theta. So what we get? We got f of r equal to minus b square plus 1 m h square by r cube. Again, it is proportional to 1 by r cube. Second trick, if the given trajectory is like this, that is r raised to n is equal to a cos n theta, or r raised to n is equal to a sin n theta, then the f of r will be proportional to minus 1 by r raised to 2n plus 3. For example, in the previous example problem, r equal to a cos theta. Here, r raised to 1 cos 1 theta, right? And we got f of r equal to minus 2m h square a square by r raised to 5. Here, what is the value of n? That is 1. So you just substitute this value here, you get the same proportionality, right? But the limitation of this trick is you can find out only the proportionality. You can find out the exact constant and all. Okay. Condition for stable orbit. The classical mechanics lecture, I started with the stability analysis. So in the stability analysis, we used some equations for finding out the stability of a particle. The same things, nothing is different. The same thing is applicable here also for the orbits, that is orbit of planetary motions. What are those stability conditions? We need a potential. So here in this case, the potential is effective potential V effective. Okay, so first condition is dou V effective by dou R equal to 0. So from this equation we get slope is equal to 0. When slope is equal to 0, that is a equilibrium point, right? So from this equation we can find out the R value. Now we have to check whether this equilibrium point is stable or unstable. So we have to take second derivative, that is dou square V effective by dou R square. And if it is greater than 0, then it will be a stable orbit. That is the condition for stable orbit is dou square V by dou R square should be greater than 0. Let us consider a general force, that is f of r is equal to minus k r raised to n. So this minus n represent it is an attractive force, and r raised to n may be anything. So it can be inverse square law force or square law force, anything. Okay. So if we know the force, we can find out the potential V of r, that will be equal to minus integral of f of r dr. That is equal to minus integral of f of r is minus k r raised to n dr. So we get k r raised to n plus 1 by n plus 1. Here k is a constant and n plus 1 is also constant. So I am rewriting this as a r raised to n plus 1. And we know the effective force V effective is equal to V of r plus L square by 2m r square. Here also you can see this L square by 2m is a constant, and I am rewriting this as B. So I can rewrite this V effective, that is equal to V of r, we already know, that is a r raised to n plus 1 plus b r raised to minus 2. Now we have to check for the stability of this orbit, that is dv effective by dr, that is equal to n plus 1 a r raised to n minus 2b r raised to minus 3. We have to find out the equilibrium point, right? So we have to equate this equal to 0. So I can rewrite this equation as n plus 1 a equal to 2b r raised to minus n plus 3. Now we have to take the second derivative of this function and we have to check whether it is greater than 0. If greater than 0, then we can say that orbit is a stable orbit. So we have to take d square v effective by d r square, that is equal to n plus 1 into n a r raised to n minus 1 plus 6b r raised to minus 4. Now we have to substitute this condition in this equation. That is, here you can see n plus 1 a can be replaced by this equation, that is equal to 2b r raised to minus n plus 3 into n r raised to n minus 1 plus 6b r raised to minus 4. From this equation, we got the equilibrium value of r, that is r equal to r0. So this will be r0, this will be r0, this also r0. And we get this is equal to 2b r0 minus 4 into n plus 3. You just do the mathematical manipulation, you get this answer. And this is d square v effective by dr square, and for a stable equilibrium it should be greater than 0. So for this term should be greater than 0, this term, that is n plus 3, should be greater than 0. Therefore we can say n should be greater than minus 3. Then only we get dou square v effective by dou r square is greater than 0. So the condition for stable orbit is n greater than minus 3. Condition for closed orbit. The general form of force is f of r equal to minus k r raised to n. Earlier we found that if n is greater than minus 3, it will be a stable orbit. And for closed orbits, the value of n should be equal to 1 or should be equal to minus 2, where when n equal to 1, the force will be corresponds to Hooke's law. And when n equal to minus 2, the general form of force will be, it's a gravitational force. One example problem. A force is given, that is F is equal to k by r raised to 3 minus n. Then find n for closed orbit. How we can solve? Here we know F is equal to, I can rewrite this as r raised to n minus 3. So this is the entire n term, and we know for closed orbits n should be equal to 1, that is this value n minus 3 should be equal to 1. And another case is n minus 3 should be equal to minus 2. So from this equation we get n is equal to 4, and from this equation we get n equal to 1. So these are the conditions for closed orbits for this given force. This one is a previous set question, and I think you can easily identify the answer, right? Answer is option C. Kepler's laws. First one, law of elliptical orbits. That is, every planet moves in a elliptical orbit around the sun. And sun will be in one of the foci. So it have two focus and sun may be in any one of these foci. Okay. And the point in the trajectory which is closer to sun is called perihelion. And the point in the trajectory which is farther to sun is called aphelion. Now second law, that is law of areas. That is, planet shifts equal areas in equal interval of time. Here this is the sun and this is our planet. Okay, it is moving from here to here. So it saves some area A, and when it is farther to the sun, it will save some area. And this is A prime. And if the time taken by the planet for the both case is same, then area A will be equal to A prime. That is, when the planet is nearer to sun, it will move with a high velocity. And when it is farther from sun, it will move with a low velocity. Then only the planet saves equal areas in equal interval of time. And from this geometry we can find out dA by dt, that is rate of change of area, that we will get as 1 by 2 into r theta dot, that is equal to L by 2m. And we already discussed the Lagrangian for central force. In that Lagrangian, theta is cyclic coordinate, so p theta is a constant value, and we got p theta is equal to m r square theta dot, that is L equal to m r square theta dot, and I told you it is a constant value. So L is a constant value, so this will be constant. That is, rate of change of area is constant. That is the law of area. Third one, harmonic law. That is, square of time period is equal to 4 pi square m by k into a cube. So I can say t square is proportional to a cube. Here t is time period, m is mass of the particle or mass of the planet, k is force constant, that is, we know gravitational force F of r equal to minus k r raised to minus 2. So this constant is this one, and a is semi-major axis. If you draw a vertical and horizontal lines like this, then this is called B, that is semi-minor axis, and this is called A, that is semi-major axis. These are previous set questions, and the first question is, the distance covered by moon each day is greatest when moon is nearer to the planet, because then only the area ship will be equal. And the second question, yeah, definitely it is r cube proportional to t square. In this question, A satellite is moving around a planet in a circular orbit and its radius is given, that is r, and the time period is t. Now the r is increased to 4r. Then what will be the time period? That is the question. From harmonic law we know t square is proportional to a cube. Here a is r itself, that is t square is proportional to r cube. So I can make two equations, that is t1 square proportional to r1 cube and t2 square proportional to r2 cube. Now I am dividing one by another, that is t2 by t1 square is equal to r2 by r1 cube. Here this one is the r1 value, initial value, and this is the r2 value. So the relation we know, that is t2 by t1 all square is equal to r2 by r1, that is equal to, here r2 is 4r by r all cube. So t2 by t1 all square is equal to 4 cube, that is t2 by t1 is equal to 4 raised to 3 by 2, that is equal to 8. So we get t2 is equal to 8t. That is option C, right? This one is a previous net question, and here one potential is given, that is V of r equal to minus k by r raised to n, and it is specified n is between 0 and 2, that means n is equal to 1. So this potential V of r is equal to minus k by r, and the question is to find out time period of circular orbit of radius r and 2r. So when r, the time period is t1, and when 2r, the time period is t2, and the question is to find out t2 by t1. Are you feeling it is a very difficult problem? Hey, don't worry, nothing is there. In the first class itself I told you about stability analysis. This is nothing but stability analysis. You can solve easily by stability analysis. So how we can solve? So here it is about orbit and all. So we have to consider the effective potential. That is V effective is equal to L square by 2m r square minus k by r. And in the question itself it is specified this is a circular orbit. And we know circular orbit is a stable orbit. Therefore, dou V effective by dou R should be equal to 0. So, what is dou V effective by dou R? This is equal to minus L square by m r cube plus k by r square equal to 0. Here I tell you another method of solving this problem. You take this equation, that is you get L square by m r cube equal to k by r square. So from here you can find out L square equal to k m r, and you can equate this L value with the angular momentum in a circular motion, that is L is equal to m omega square r. So you can equate equation 1 and 2 and you can find out the answer. And I give you this as a work for you. You please follow this method also and try to find out the answer. And here I tell you one more thing, that is omega is, we know it is equal to 2 pi by t. So we can make a relation between time period t and r. Okay, you please try this. Now I am following this method. that is stability analysis method. So I am taking the second derivative of this function, that is dou square v effective by dou r, that is equal to 3l square by m r raised to 4 minus 2k by r cube, that is equal to 3 by r into l square by mr cube minus 2k by r cube, where l square by mr cube is equal to k by r square, that is equal to 3 by r into k by r square minus 2k by r cube. That is, we get dou square v effective by dou r square is equal to k by r cube. And from this equation we can find out omega, that is omega is equal to root 1 by m into dou square v effective by dou r square. So we get this is equal to root 1 by m into k by r cube. And we know time period t equal to 2 pi by omega, that is equal to, we get 2 pi into root m r cube by k. That is, we got time period t is proportional to r raised to 3 by 2. So I can make two equations, that is t1 is proportional to r1 raised to 3 by 2 and t2 proportional to r2 raised to 3 by 2. Now I am dividing these two equations, that is t2 by t1 is equal to r2 by r1 all raised to 3 by 2. Now we can substitute the value of r2 and r1, that is t2 by t equal to 2r by r all raised to 3 by 2. So we get the relation t2 by t1 is equal to 2 raised to 3 by 2. And here when solving this problem, we know n value is equal to 1. So now check the options, which one will give 2 raised to 3 by 2 when substituting n equal to 1. So that will be the answer. So in the option C, if you substitute n is equal to 1, you get 2 raised to 3 by 2. Okay, so the answer is option C. Trajectory under central force. What will be the trajectory if the force is a central force? That is, if force, that is f of r is equal to minus k by r square, that is our gravitational force, then what will be the trajectory? Then the trajectory will be a conic, and the equation of trajectory is 1 by r equal to 1 by l into 1 plus e cos theta, where we call e as eccentricity and its value is equal to root of 1 plus 2m e h square by k square, where we know h is equal to L by m and here L is equal to L square by mk. Now from the equation of eccentricity, we can deduce the following conditions. That is, first one, if eccentricity is greater than 0, then the trajectory will be a hyperbola and its energy. So from this equation, we can find out the energy, and that energy will be greater than 0. And another case, E equal to 1, then the trajectory will be a parabola. And for this case, E is equal to 0. So from the ideas of stability analysis, we can say these are unbound motion. And this eccentricity may be less than 1. Then the orbit will be ellipse. That is, energy will be equal to negative. And another case, maybe eccentricity is equal to 0. Then the trajectory will be a circle. And here also energy will be negative. So we can say these are bounded motions. See, these orbits, that is elliptical orbit and circular orbits, are closed orbits. So it is a bounded motion. Okay. Now we are going to discuss about planetary motion and conservation laws. And you know, the planetary motion is in a elliptical orbits, right? So for planetary motions, the orbits look like this one. And the elliptical orbit will have two focus, and our sun will be at one of the focus, right? So this one is our sun, and I'm considering our earth is revolving around the sun. So I'm taking two extreme positions. One is aphelion and one is perihelion. And I'm taking this distance as A and this distance as B. For this earth, at distance A, it will have a velocity, and I am calling its velocity as v1. And when it is at distance B, it will have a velocity, and I am calling that velocity as v2. And from the law of areas, we can definitely say v2 will be definitely greater than v1. Yeah, then only it will seeds equal areas in equal interval of time, right? Position A, it will have a kinetic energy that will be equal to half m v1 square. Kinetic energy will be equal to 1 by 2 m v2 square. Here this potential energy is equal to minus g m by the distance, that is here is b. And here the potential energy will be equal to minus g m by the distance, that is a. Now I am going to find out what is the law of conservation of energy for planetary motion. That is, A will be equal to its energy when it is at position B. So I can add this kinetic energy and potential energy, and I can equate it to these two values. So what we get? We get 1 by 2 m v1 square minus g m by A is equal to 1 by 2 m v2 square minus g m by B equation. Now I am taking this 1 by 2 m as a common term, so I get v1 square minus v2 square is equal to g m into 1 by A minus 1 by B. Once again I am rearranging, that is 1 by 2 m v2 square minus v1 square is equal to g m into A minus B by AB. So we get v2 square minus v1 square is equal to 2 gm into A minus B by AB. So we got relation between v2 and v1 from law of conservation of energy. Next I am considering law of conservation of angular momenta. We already discussed under central force, the angular momentum L is constant and that is equal to mr square theta dot. That is equal to mr square omega. Theta dot is nothing but omega. And we know omega is equal to v by r. So we get this is equal to mvr. I told you this is our elliptical orbit, and when the planet is at this position, it will travels with the velocity v2, and this distance is b, and this distance is a, and the velocity is v1. So the angular momentum will be conserved, that is L1 will be equal to L2. So we can write m v1 a is equal to m v2 b. So we can cancel this m and we get v2 by v1 is equal to a by b. That is v2 is equal to v1 into a by b. Right. Now I am going to substitute this condition in our earlier equation, that is v2 square minus v1 square is equal to 2gm into a minus b by ab. Now I am substituting this equation in v2 square. So what we get? We get v1 square a square by b square minus v1 square equal to 2gm a minus b by ab. That is equal to v1 square into a square by b square minus 1 is equal to 2gm into a minus b by ab. That is v1 square is equal to 2gm a minus b by ab into b square by a square minus b square. So here we can cancel one of these b, and we can again rewrite this as 2gm into a minus b by a into b by a minus b into a plus b. So a minus b and a minus b will cancels, and we get v1 square is equal to 2gm b by a into a plus b. So we can say v1 is equal to root of 2gm b by a into a plus b. Then what will be the value of angular momentum? That is, we now L is equal to mvr. Here we know the v1, that is mv1. When it is v1, the distance is a. So we can substitute this v1 here. So we get m into v1, that is root 2g mb by a into a plus b into a. So here one a is there. So we are taking this a inside. So finally we get L equal to root 2g m square ab by a plus b. Then what will be the total energy? That is, we know total energy E equal to kinetic energy plus potential energy. So what is kinetic energy? Half m v square. Here I am taking v1 square, and potential energy is minus g m by when v is v1, the position or the distance will be a. And we know the value of v1 square, that is equal to 1 by 2m into 2gmb by a into a plus b minus gmm by a. Now here we can cancel this 2 and 1 by 2, and I'm taking the common term, that is GMM by A into B by A plus B minus 1. And by expanding this one, we get B minus A minus B by A plus B. That is equal to minus A by A plus B. So we get total energy E equal to minus GMM by A plus B. Now I am going to summarize all these equations. That is, for elliptical orbits, we know A is not equal to B, and then the first equation, that is V2 square minus V1 square, will be equal to 2gm into A minus B by AB. And second equation, that is V2 by V1 is equal to A by B. And third equation is equal to root 2g m square AB by A plus B. And fourth equation is total energy E is equal to minus g mm by A plus B. So all these equations are for elliptical orbit, and for elliptical orbit A is not equal to B. Then what will be the corresponding equations for circular orbits? And for circular orbits, we know A is equal to B. Then what will be the first equation? That is 1 become V2 square minus V1 square will be equal to 0, because A and B are same, right? And second equation will be V2 by V1 will be equal to 1. And third equation, angular momentum L will be equal to Gm m square R. And equation for energy will be equal to E equal to minus Gm m by 2R. This one is a previous net question, and we discussed the total energy of the planet is minus Gmm by A plus B. See, this one is another net question, and the question is the angular momentum of the planet. We already discussed this one also, right? That is option D. This one is a previous CSIR net question, and it is a part C problem also. The question is, Mangalyaan is into Mars and it traces a elliptical orbit. Okay, and for this elliptical orbit, you can see Sun is at one of the focus. Okay, and this distance is given, that is RE. And this distance is given, that is RM. And they are asked to find out the velocity of this Mangalyaan at distance in between RE and RM. So at this position, we have to find out this velocity. That is the question. And in the question, this is R, and R is greater than RE and less than RM. So we have to find out the velocity when the Mangalyaan is at position R, right? So at position R, we can find out its total energy, that is total energy E equal to kinetic energy plus potential energy. So that is E equal to kinetic energy, that is 1 by 2, here velocity is V, so V square, potential energy is minus G m by R, because R is the position. And we know the energy in an elliptical orbit, that is E equal to minus G m by A plus B. And here we know A is equal to RM and B is equal to RE. So we can substitute these values, that is Rm plus Re. Now we can equate this equation 1 and 2. That is 1 by 2 m v square minus g mm by r is equal to minus g mm by re plus rm. So from this equation you can find out for the v. So you please do this. This is a work for you. So finally you will get this answer. Okay. Virial theorem. This theorem relates average value of kinetic energy and average value of potential energy. That is f of r equal to k r raised to n. Then the average kinetic energy of the particle moving in this force will be equal to n plus 1 by 2 of average value of potential energy. So this relates the average value of potential energy and kinetic energy under a central force. Now let us consider some examples. First one is gravitational force. Now it is a central force, that is F is equal to minus g m by r square. So what is the n value? N value is equal to minus 2. So by using this equation, that is average value of kinetic energy equal to n is minus 2 plus 1 by 2 into average value of potential energy. So what we get? So we get kinetic energy is equal to minus 1 by 2 average value of potential energy. So for the gravitational force, this is the relation between kinetic energy and the potential energy. Now second example, that is harmonic oscillator. That is for harmonic oscillator, F is equal to minus KR, that is n equal to 1. So what we get? We get average value of kinetic energy equal to 1 plus 1 by 2 into average value of potential energy. That is average value of kinetic energy is equal to average value of potential energy for harmonic oscillator. This one is a previous gate question, and here a satellite is moving in a circular orbit and they are asked to find out the relation between potential energy and the total energy. So definitely here the force is gravitational force, and for gravitational force we know the relation between kinetic energy and potential energy, that is average value of kinetic energy will be equal to minus 1 by 2 average value of potential energy. This is for gravitational force. And here in this question they are using T for kinetic energy and V for potential energy. That is average value of T is equal to minus 1 by 2 average value of V. And they are asked to find out the total energy, that is kinetic energy plus potential energy. And in the options they given the potential energy, so we have to find out corresponding kinetic energy. Then by adding these two we can find out the total energy. Okay, so first I am checking the first option, that is V is given, that is equal to minus 2t. So we can find out the average value of t, that will be equal to minus 1 by 2 into minus 2t, that is t. So we can find out the total energy, that is equal to t plus v, that is E equal to t. Here average value of t is t itself, t plus average value of V, that is minus 2t. So we get it is equal to minus t. So for V equal to minus 2t, we got E equal to minus t. So the option A is the correct answer. This one is a previous net problem, and in the question the potential is given, that is V equal to A r raised to 6, and the question is to find out the ratio of kinetic energy to its total energy. So how we can solve this? We know Virial theorem, that is for a force f of r is equal to kr raised to n, then average value of kinetic energy is equal to n plus 1 by 2 average value of potential energy. So in the question they given the potential, so from the potential we can find out the force. So we can find out the relation of n, that is f of r is equal to negative gradient of potential, that is equal to minus 6a r raised to 5. So we got the n value, that is n equal to 5. Now we can substitute in this equation, that is kinetic energy is equal to n is 5 plus 1 by 2 into average value of potential energy, that is V. So here we got average value of kinetic energy is equal to 3 into average value of potential energy. And we know total energy E equal to kinetic energy plus potential energy. So we get total energy E equal to kinetic energy is 3V plus potential energy is V. So we get total energy is equal to 4V. Now we can find out kinetic energy by E, that is kinetic energy is equal to 3 average V by total energy is equal to 4V, that is 3 by 4. That is option C.